Hello, in this video, we are going to talk about Module 4, System Modeling using UML or Unified Modeling Language. In this module, we will talk about different types of models we use in system modeling with UML. We will start with context models. These help us understand how the system fits into its environment, what external entities interact with it, like users or other systems. And it gives us the big picture. Next, we will have interaction models. These are really useful for visualizing how different parts of the system or the system and the user communicate with each other. Then we will go to structure models. This shows the organization of the system, like classes, objects, and how they are related. And after those, we will look through the behavior models, which is a focus on what the system does over time, and model-driven engineering. This is more advanced. It is an approach where models aren't just documentation, they actually drive the development process. In other words, we generate code or system artifacts directly from the models. And now for tools, you can use Asta, which you can download from asta.net, or you can go with draw.io, which is a great online option. It's simple, intuitive, and works well for UML diagrams if you don't want to install anything. So there are very different websites and tools. These are two examples of those. Let's talk about a bit about what system modeling actually involves. At this core, system modeling is about creating abstract models of a system. And by abstract, we mean simplified versions that highlight specific aspects of the system. Each model gives us a different perspective. For instance, one model might focus on how user interact with the system, while another might show how components are structured behind the scenes. Now, why we do this? There are a few reasons. First, these models help us communicate more effectively with stakeholders, especially customers who may not understand the technical side. Showing them a diagram or a simple interaction model is often much clearer than trying to explain everything verbally or with code. Second, it's a huge help for analysts and designers. These models give them a clearer understanding of the system's functionality before any code is written. It's like planning the blueprint before building a house. And how we do usually represent these models through graphical notation, most commonly using UML or Unified Modeling Language. UML is a standardized way to visually represent different aspects of a software system. And we will be working with several types of UML diagram throughout the course. Although now let's dive into different perspectives we can take when modeling a system. Each perspective gives us a different angle on how the system behaves, interacts, or is structured. First, we have the external perspective. This is all about modeling the context, basically the environment in which the system operates. We look at how the system interacts with external actors like users, hardware, or other systems. It helps us define system boundaries. Then there is interaction perspective. Um, this one zooms in a bit more on how different parts of the system or the systems with and its environment communicate. For example, when a user clicks a button and the system sends a confirmation, that's an interaction. We also look at how internal components talk to each other. Next is the structural perspective. Here we are looking at the architecture of the system. What are the main components? How are they organized? And how is the data structured and passed around? Think of it as a systems skeleton. And finally, we have the behavioral perspective. This is where we model the system's dynamic behavior, how it responds to inputs, how it handles events, and what actions it performs under different conditions. This is where state diagram and activity diagrams often come into play. Together, these perspectives give us a comprehensive understanding of the system, kind of like viewing it from multiple camera angles. Now let's take what we just learned about the four modeling perspective and apply them to a real world example, specifically the MHCPMS system, which is a mental health care patient management system. So starting with the external perspective, we want to ask what other systems are part of the environment in which MHCPMS will operate. For example, are there hospital databases, billing systems, or appointment schedulers that this system needs to interact with? This helps us understand the boundaries of our system and its dependencies. Next is the interaction perspective. Here, we are looking at how users interact with the system. So we might ask, what does the doctor or receptionist do in the system? How do they enter patient data or view reports? Also, don't forget about other systems. Maybe there is a lab system that sends test results to MHCPMS. All of these are interaction points we need to model. Moving on the structural perspective, this is where we get more technical. We ask questions like what classes or objects are needed for the system to work. For example, we might have patient appointment and prescription classes. We also want to think about how our database is structured and how it maps to these objects in the code. And finally, the behavioral perspective focuses on how the system behaves in response to events. A good question here might be what happens in the system when we add a new patient? Does it validate the model, assign an ID, update the records, and maybe notify the assigned doctor? All of these steps are part of the system's dynamic behavior, and they are exactly what we capture in behavioral models. So this slide is essentially a checklist of key questions we should ask for each perspective when modeling any system. Let's go over some of the key types of UML diagram that we will be using when modeling system. We will start with use case diagrams. These are great for showing how users or external systems interact with the system. They are high level and they help answer questions like what can the user do with this system? Think of it as a way to capture user goals or system functionality from an external point of view. Next are sequence diagrams. These are more detailed and focus on time-ordered interactions. For example, how a user request triggers a series of internal operations. They show both interactions between users and the system and also interactions between components within the system, like how one model might call another. Then we have class diagrams, which are the backbone of object-oriented modeling. These diagrams show the system's classes, their attributes, methods, and how they relate to each other. They are essential for a structural model. Activity diagrams come next. These are similar to flowcharts. They show the flow of actions in process, whether it is a business workflow or a step-by-step algorithm. They are really helpful for modeling logic and parallel activities in data processing. And finally, we have state diagrams. These focus on how a system behaves in response to events. For example, when a user submits a form, what changes in the systems? In that system, does it move from an idle state to a processing state? These diagrams are great for modeling components that go through various states over time. Each of these three diagrams offers a different lens of analyzing, designing, and communicating how a system works. You don't have to use all of them in every project, but knowing each of them fits which purpose is key. This diagram is a really helpful summary of how different UML tools align with the perspective we have been discussing. Let's start with the interaction perspective. This view focuses on how users or systems interact with the software. To model this, we commonly use use case diagrams which capture high-level functionality, and sequence diagrams which dive deeper into how interactions flow over time, step by step. Next, we have the structural perspective. This is all about how the system is organized internally, its architecture, components, and data structure. The main UML tool for this is class diagram, which shows classes, their attributes, methods, and how they are connected. And then there is a behavior perspective. This one looks at how the system acts, how it behaves in different situations or in response to different events. To model this, we use state diagrams which show the different states an object or system can be in, and activity diagrams which help us visualize workflow or processes. So basically, for each perspective we take during system modeling, there are specific UML diagram types that help us describe and document the view clearly and accurately. This slide focuses on something really important in system modeling, the operational context. When we model a system, we don't just care about what happens inside the system. We also want to show how it fits into the bigger picture. So one thing we often do is create a context diagram. This helps illustrate what's outside the system's boundaries. In other words, it shows what other systems, users, or organizers interact with it. It's a static view, meaning we are not showing dynamic behavior here, just a structure of how things connect. These diagrams are useful because they show the system's relationship with other systems, whether that's a paying processor, a database, or even a manual process handled by a human. It gives stakeholders a shared understanding of what's inside and what's outside the system we are developing. And lastly, something that's often overlooked but very real, social and organizational concerns, which can affect how we draw these boundaries. Sometimes, due to internal politics and regulations or how departments are structured, we may need to adjust where those boundaries go, even if it is not the most technically efficient setup. So this kind of model helps us step back and see the system in context, not just as a piece of software, but as a part of a larger environment. Here we have a context diagram for MHCPMS program, which stands for Mental Health Care Patient Management System. This diagram gives us a high-level view of how our system interacts with its external environment. At the center, there is a MHC PMS we have that's the system we are designing or analyzing. Surrounding it are all the external systems it needs to connect with in order to function properly. So, for example, it interacts with the patient record system, which stores long-term patient data, and the admission system, which handles patient check-ins and onboarding. Then we have got the prescription system, which might be used by doctors to send prescriptions electronically. It also connects to the appointment system for scheduled visits and the HC statistics system, which could be government mandated reporting system that collects data for health analytics. Then on the left side, we see management reporting system, which could be used by administrators or department heads to track performance, budgets, or resource usage. This kind of diagram is really useful because it shows us what lies outside the boundaries of our system, but it still needs to be considered during development. It helps identify integration points and clarify responsibilities, what data we need, where it comes from, and who we are sharing it with. So again, this is a static view. So we are not looking at how data flows or what order things happening, just the big picture of system relationship. Now let's talk about interaction modeling, which is a key part of understanding how a system communicates both internally and externally. There are a few different levels we want to think about here. First, we have user interaction with the system. This is all about how users like doctors, receptionists, or even patients engage with the interface or features. What actions are they taking? What feedback do they expect? Use case diagrams are specifically helpful here. Next, we have the system to system interaction. So rather than a person using the system, now we are looking at how two systems communicate. For instance, the MHC PMS might send patient records to an external prescription system or fetch data from a hospital database. We need to capture and model those kind of interactions as well. Then there is component interaction, which dives deeper into how different parts of the same system talk to each other. This is important during system design because it helps us figure out whether the proposed structure will actually support the performance and behavior we need. If components aren't interacting properly, the whole system might become inefficient or prone to errors. To model all of these interactions, we typically use use case diagrams and sequence diagrams. Use case diagrams give us the high level overview of functionality and actors, while sequence diagrams let us see the detailed step-by-step interactions over time. So think of this slide as a checklist. Who's interacting? Is it a person, another system, or an internal component? And then how are we going to model that? So now let's talk more about the use case. These are one of the fundamental tools in UML modeling. Each use case describes a single specific feature of the system that's triggered by an external interaction. Think of it like a function that system provides to an outside actor. For example, login, schedule appointment, or transfer data. Each of these could be its own use case. Now, when we talk about actors in a use case, we are not just talking about people. An actor can be a role like doctor, receptionist, or it could be another system that interacts with our system. For instance, if MHC PMS system connects to a statistics system, that external system might also be considered an actor. In the context of MHCPMS, a common use case might be something like transfer data, which could involve sending patient reports to another hospital, exporting files for backup, or reporting statistics to a national health database. We will walk through that example in more detail in the next slide. Here we have a concrete example of a use case for MHC PMS system. It's called transfer data. Let's walk through the key elements of this use case one by one. The actor involved are the medical receptionist and the patient record system, or PRS, which is another system the MHC PMS interacts with. The description give us a clear picture of what's happening. The receptionist is sending patient information from MHC PMS to a central database, typically managed by a health authority. This could include updates to personal details like address or phone number or medical data like diagnosis and treatment summaries. Next, we have data being transferred. This include both the patient's personal information and a treatment summary. So we are dealing with sensitive data here, which is why the process must be carefully managed. And the stimulus is a user command issued by the receptionist. So the action starts when the receptionist initiates the transfer. Then comes the response. The system confirms that the patient record system has been updated successfully. That's important feedback so the user knows the operation went through. And finally, a quick note under comments, the special receptionist must have the proper security permissions to access this information and to interact with the PRS. This ensures we are complying with data protection and privacy policies. So this use case not only models system behavior, but it also reflects real-world constraints and requirements like user rules and security. All right. Here we have a use case diagram showing the different actions a medical receptionist can perform in the MHC PMS system. Remember, in UML, the little stick figure here represent an actor. So in this case, the receptionist. Each oval represent a use case, a function or service the system provides to the actor. So what can the medical receptionist do? They can register a patient, which likely involves entering demographic and insurance information. Unregister a patient, maybe when someone moves to another provider or no longer uses the service. View patient information, which could include medical history, contact details, or appointment status. Transfer data, like we discussed earlier, sending patient record to another system, and contact the patient, which might be used to send reminders, follow-ups, or emergency messages. So each of these interactions is something the receptionist initiates and the system responds accordingly. Now let's move on to sequence diagrams, which are a type of interaction model in UML. These diagrams are really useful because they let us model the interactions between actors and objects within the system. So unlike use case diagrams that just show what happens, sequence diagrams show how it happens step by step. They capture the sequence of interactions that take place during a use case. In other words, they show who talks to whom, in what order, and what messages or operations are being exchanged. At the top of the diagram, you will usually see a row of objects and actors involved in the process. For each one, there is a dotted vertical line, or we call it a lifeline, and it represents the timeline for the object or actor. Here's a great example of a sequence diagram in action. This one models how a medical receptionist requests to view patient information in the MHC-PMS system. Let's walk through it step by step. On the top row, you can see actors and system components involved. The medical receptionist, the patient info object, the MHC PMS DB, which is the systems database, and the authorization service. Each vertical line represents a lifeline, and the arrow between them show how messages flow in time from top to bottom. So it starts with the receptionist sending a view info request along with the PID, which is a patient's ID, to the patient info object. That request gets forwarded as a report message to the MHC PMS database, including info, the patient ID, and the user ID of the person requesting access. Before any data is written, the system checks authorization. So it sends a message to the authorization service asking whether this user is allowed to view that information. And now here is the interesting part. This box labeled alt stand that stands for an alternative flow, meaning there are two possible outcomes based on whether authorization is successful or not. If authorization is okay, the system proceed to return the patient info back to the receptionist. But if authorization falls, it returns an error saying no access is guaranteed. So this sequence diagram helps us to see both the normal flow and the exception flow all in one place. It's really powerful way to represent what's going on behind the scene when a user interacts with the system. That's example 2 of a sequence diagram, and this one is a bit more detailed. It showed the process of transferring data from the MHC PMS to the patient record system, or PRS. At the top, we have our actors and components, the medical receptionist, P, which is patient info, the interface handled patient data, D, which is a database for the system, and AS, authorization, which is the service that checks permissions, and on the far right there is an external PRS system. Let's break this down. The process starts when the receptionist logs in and initiates one of two possible actions: send info and send summary. So this is captured using the alt box again, that means alternative passes. So depending on the scenario, either one of these flows is followed, as you can see in this diagram here. So everything here shows a clear step-by-step interaction between internal components and an external system with built-in security checks along the way. It captures both functional behavior and non-functional requirements like authorization and confirmation messages. All right. Now let's talk about structural modeling, specifically how we use it to design and understand the system architecture. This type of modeling is really helpful when we want to visualize how a system is organized. We are looking at things like what components exist, how they relate to each other, and how we might build the overall structure. In object-oriented systems, these components are usually represented as classes. So a structural model describes the system in terms of its classes and the relationships between them. That could include associations, inheritance, composition, whether applies to your design. Now, when we are developing a structural model using UML, we typically use a class diagram. This shows all the classes involved in the system and the associations between them, who talks to who owns who, and how everything is connected. Let's talk a bit more about associations in UML, specifically in the context of class diagrams. An association is simply a link between classes. It shows that there is a relationship between them. For example, if you have a doctor class and a patient class, and the doctors treat patients, you would represent that with an association line connecting the two classes. Now, when we are developing models, especially in an object-oriented approach, it's helpful to remember that your object often represents things in the real world. So think about a healthcare system. We will have things like patient, prescription, doctor, appointment, and so on. So each of those real world entities can become a class in your model. And here is a neat little rule of thumb. When you are reading a problem description, look for the nouns. Most of the time, the nouns in the text point to potential objects or classes, and the verbs between them help you identify the relationships or responsibilities. So this technique can really help you break down a system and build a solid object model. This is a great example of a basic UML class diagram showing an association between two classes, patient and patient record. The line connecting them represent a relationship, and the numbers on each side indicate the multiplicity of that relationship. Here, both sides have a 1, which means this is a one-to-one relationship. So we are saying that each patient has exactly one patient record, and each patient record belongs to exactly one patient. So this kind of relationship makes sense in healthcare systems where a patient has a unique medical file that stores their complete treatment history. This diagram gives us a more complicated and complete structural model of a healthcare system, showing how different entities are related. Let's start in the center with the patient class. So, because everything else kind of branches out of from here. So, a patient is diagnosed with one or more conditions, and so here we have one more condition. And each condition must be associated with at least one patient. So that's a many to many relationship. As you see, it's mentioned one dot dot star on both ends. So that's why we have many, a star represent as many. Patients can also referred by a general practitioner, and they may be referred to a consultant. So these are one to many relationships. The GP or consultant is is on the one side, and each patient may have many such referrals. Then we have consultations. Each patient attends one or more consultations, and a consultation is always associated with at least one patient. Again, this is a one-to-many relationship. And each consultation is run by one or four hospital doctor. So this adds another layer limiting the number of doctors involving in a consultation to a max of 4. During a consultation, the doctor may prescribe both medications and treatments. These are many-to-many relationships as well. One consultation can lead to multiple prescriptions, and the same medication or treatment might be used across many different consultations. So overall, this diagram gives us a solid view of what entities or classes exist, how they are linked through associations, and their multiplicities that define how many of each object can be involved in their relationship. This is a class diagram for the consultation class, and it's a great example of how we represent both data and behavior in an object-oriented model. This class is divided into two sections. The top section lists the attributes. These are the pieces of data that each consultation object will store. So, for example, here we have doctors, date, time, clinic, which capture basic appointment information. They have reason, which could be have the why the consultation is happening, medication prescribed and treatment prescribed, voice notes and transcript, which might store audio or written records of the interactions. These attributes describe what the object knows. The bottom section lists the methods or operations. These represent what the object can do. So here we have methods like new, probably to initialize a new consultation, prescribe for generating a prescription, record notes to attach notes to the session, and transcribe maybe to convert voice notes into written text, for example. These define what the object can do, its functionality within the system. So overall, this class diagram helps us clearly model a real world entity, in this case, a medical consultation, by capturing both its data and behavior in one place. Let's talk about generalization, which is one of the core ideas in object-oriented modeling and something we actually use all the time in everyday thinking. Generalization is basically a technique we use to manage complexity by organizing things into broader categories. Instead of thinking about every individual object on its own, we create more general classes. For example, instead of listing out every specific kind of animal, we have a general class called animal. Same for vehicle, house, and so on. So these general classes help us understand and describe the world more efficiently. So now why does this matter in software? Because when we design systems, we do the same thing. We group objects into general classes, and from there, we can define shared characteristics and behaviors. It's way more scalable and reusable than handling everything individually. And members of a general class usually have some common features, like in the slide, all vehicles have things like a fuel type, engine power, and max speed. So that means we can define those shared attributes in a base class and then inherit them in more specific types like car, truck, or motorcycle. So generalization is really just another word for inheritance in UML, and it helps us build cleaner, more modular designs. Now let's build on what we just discussed about generalization by connecting it to how we actually use it during structural modeling. When we are analyzing system requirements, one of the first things you should do is look at the different classes and ask, can any of these be generalized? A simple way to spot that is by looking for is a relationships in the requirements. For example, if the text says a truck is a vehicle, that's a big clue that inheritance should be used. Generalization in UML is implemented using inheritance, which is a built-in mechanism in all major object-oriented languages like Java or C Sharp. It lets us define common attributes and behaviors once in a base or parent class and reuse them in subclasses. So if we have a general class like vehicle and subclasses like car and truck, we can define shared attributes like engine power, fuel type, or max speed in vehicle, and they all automatically apply to all vehicles. So then in the lower level classes, we can add more specific attributes or behaviors. For example, truck might have load capacity, which wouldn't apply to a car. The point is, this helps us avoid repetition, manage complexity, and keep our designs organized and scalable. This diagram is a classic example of generalization in the UML, and it shows how we can structure a class in hierarchically using inheritance. At the top, we have the most general class, doctor. This class would include attributes and methods that apply to all types of doctors, like name, ID number, specialization, or a method like prescribe. From there, we have two direct subclasses, hospital doctor and general practitioner. Both of these inherit from doctor, meaning they get all of its properties and behaviors by default, but they may also have their own additional features. For instance, a hospital doctor might work in a ward, while a general practitioner runs a clinic. Now let's go a level deeper under hospital doctor. This branch splits into consultant and team doctor, and the team doctor class itself further specialized to trainee doctor and qualified doctor. So each level down becomes more specific. The base class doctor defines shared attributes, and as you move down the tree, subclasses added their own unique details or override inherited behaviors. This is a great way to manage complexity in your system rather than rewriting the same data and logic for every kind of doctor. We build it once and reuse it through inheritance. This diagram is a great example of how inheritance works in UML class modeling. So at the top, we have the general class, doctor. This class contains shared attribute like name, phone number, email, and it also refers to the common operations that all doctors can perform, such as register and deregister. So as we saw in the previous slide, we have two specialist subclasses, hospital doctor and general practitioner, and each one has specific attributes. For example, a hospital doctor has a staff number and a pager number. A general practitioner has a practice name and address. So this diagram shows how inheritance supports reuse and specialization in object-oriented designers. Now we are looking at composition and aggregation, a key concept in instructional modeling. This slide introduces the idea that some classes are made up of other classes. In other words, a class might not just store data, it might contain other objects as part of its structure. This is often called a part of relationship in data modeling. So, for example, a car has an engine, a library has books, a hospital has departments. In UML, we represent this relationship using aggregation or composition. depending on the strength of the relationship. But the key idea is one class is made up of smaller parts that are themselves classes. In software requirements, you can usually spot this by looking for has a phrasing. So when you see something like a patient record has a list of visits, or a consultation has a doctor and notes, that's a strong signal that you are dealing with composition. This approach helps break down large complex systems into manageable modular components, just like generalization helps with organizing related types. This diagram shows a great example of composition in UML, where one class is made up of other classes. In the center, we have the patient record class, which is the whole. It's composed of two parts, a patient and one or more consultations. Now, notice the diamond symbol in UML. A filled diamond would mean strong composition, meaning the parts cannot exist without the whole. Here we see empty diamonds, which indicate aggregation. A loser has a relationship, but still showing structural connection. The labels explain the relationship. A patient record is composed of exactly one patient. That's the one-to-one relationship on the left. And a patient record contains one or more consultations, which is a one-to-many relationship on the right. So each patient record belongs to one patient and it includes multiple consultations. This model helps us structure how the system stores related information, especially when we are thinking in terms of real-world objects. Let's shift the focus now from structure to behavior. This slide is about modeling the dynamic behavior of a system. That is what the system does while it's running. In dynamic modeling, we are not just looking at what a system is, but what it does. Specifically, we are asking what happens when the system receives input from its environment. This input is called a stimulus, and the model shows how the system reacts. Now, there are two types of stimuli, data stimuli and event stimuli. So in the data stimuli, that's information that the system needs to process. For example, a user submitting a form or uploading a form. Even the stimuli are more like triggers. They kick off a specific behavior or action in the system. Think of a timer expiring, a button click, or a sensor going off. These kind of models are useful in capturing real-world interactions, especially for systems where behavior depends on timing or sequences of inputs, like in embedded systems, user interfaces, or even medical record systems like we have been seeing. And UML helps us visualize this using tools like state diagrams, activity diagrams, or sequence diagrams, which we will explore next. This diagram is a great example of dynamic modeling. It shows how a system responds to input and processes data step by step. We are looking at an automated insulin delivery system, and the flow starts at the top left with the blood sugar sensor. First, the sensor detects the current blood glucose level, and the system reads that value and convert it into usable sensor data. Then it computes the sugar level, and we store that as a blood sugar level. At this point, the system reacts to that input. It needed to calculate how much insulin the patient needs. So it performs a calculation for insulin delivery, resulting in an insulin requirement. Now the second half of the process builds. Um, this is begins with where the system prepare to act based on the calculations. So it calculates the control command and that the pump will use. These are converted into a specific pump control command, and the system then uses those to control the pump and also send insulin through the insulin pump. So this entire flow illustrates how a stimulus, in this case blood sugar level, triggers a sequence of actions, decisions, and responses from the system, ending with an automated physical output. Now let's talk about state machine models, which are really helpful when we want to understand how a system behaves in response to different events. We use these models when we will dealing with external and internal events, things like button press, a login request, or even a system timeout. What makes these models particularly useful is that they focus on how the system responds to stimuli. So they are often used in real-time systems where actions depend on triggers, think elevators, traffic lights, or medical devices. In a system machine model, as the system is visualized as a set of states shown as nodes. Then we use arcs or arrows to represent events that cause the system to move from one state to another. So imagine a user logs into a system. That login event causes the system to move from, for example, waiting for logging state to a logged in state. Each arrow you see represents an event, and each bubble or circle is a state. So this is a powerful way to show the flow of control, and we will use this approach whenever we want to reason about system behavior over time. So now let's take a look at this state machine diagram that models the behavior of an online order system. We start with an initial state shown here by the black circle. When an order is received, the system transitions into unprocessed order state. Now from here, the system performs a check. If the order is rejected, maybe due to invalid payment or policy violations, it moves into reject order state, which is a terminal state. That's the end of the process for the order. As you see, it goes to an end. But if the order is accepted, the system transitions to the accepted order state. From there, it branches again based on the item availability. If some items are available, it moves straight to fulfill order and the order gets delivered. If some items are not available, the system moves to a pending order state. And it's like saying we are holding your order until the missing items are restocked. So once all items become available, maybe a supplier restart, the order can be fulfilled, completing the cycle. So what you are seeing here is a great example of how events and conditions drive transitions from one state to another. Every arrow represents a state change triggered by an event or condition, and every box is a specific situation or phase the order can be. This is the power of state machines. They give us a visual way to model how a system behaves step by step as it responds to inputs. Here we have another example of a state diagram of a microwave oven. So at the initial state, you see the system starts in the waiting state, and the action is it continuously displays the time. Then we have full power or half power. And as you see, it goes over all of these states by each condition, different conditions. So at the final state, we have when the cooking ends or is cancelled, the system returns to waiting state and completing the cycle. So this diagram shows event-driven transitions like pressing a button or opening the door. There are some actions that happen in each state and control flow through real-time system states, which is ideal for embedded systems like a micro. Here we have the table provides detailed description of each state in the previous example, microwave oven's state machine diagram, offering a clearer understanding of what the oven is doing at any given moment. So we have the states, for example, waiting, and the description, which, for example, the oven is idle, awaiting a user input, display show the current time, and so on. Here we have also the states and stimuli for the microwave oven example, which we have a stimulus and the description. For example, for half power, we have a user passes the half power button, or for the stimulus full power, user presses the full power button, and so on. Okay, so here we have the key points of this section. We talked about behavioral models in software engineering, and let me just, okay, so we talked about the models, and also a model is an abstract representation of a system. A model ignores system details to focus on specific concerns. Multiple complementary models are used to give a full understanding of the system. We talked about context models, which show how the system interacts with with its environment, including other systems. Use case diagrams, which capture how users and external systems interact with the system. Sequence diagrams show detailed interactions between objects in a scenario over time. Structural models, which describes the static organization of a system, and the class diagrams, which define classes and relationships, useful for object-oriented design. And also, we talked about the behavioral models with the purpose of those is to describe the dynamic behavior of a system while it's executing and focus on how data flows through the system and what events trigger system transitions or actions. We also talked about activity diagrams, which represent data processing steps or workflows, and each activity is one step. And we talked about the state diagrams, which model how a system reacts to internal or external events. So this was the summary we have learned through this chapter, and thank you for watching this video.